Okay, y'all, let's get started. Last day, so that's right. I was going to say last day of getting up early, but that's not quite true because Thursday is another early rising day. So I've tried to soften the blow a little bit on Thursday by making the start time for the final be at 8:45 rather than at 8. So I'll see you bright and early Thursday morning in here, 8:45 for the final. It is not comprehensive. It only covers the material since the last midterm, so essentially recursion, binary search trees, AVL trees, big O notation. The one thing where it is comprehensive is I expect you to be conversant with the other data structures we covered this semester, like hash tables, double-ended queues, vectors, arrays, lists. So you still need to know when it's appropriate to use each of those data structures. You need to know what their running times are. There is a question on the final exam similar to the question on the second midterm saying here are some situations or problem scenarios. Which of the following data structures would you choose? And in addition to the data structures you had for the second midterm, you'll also have binary search trees and AVL trees for this particular exam. There's no coding questions on the exam. There are code reading questions on the exam. So I'll slightly take that back on the code writing. There's one question that says, here's an issue, read this code, there's an issue with it, fix it. Okay, so not something where you're writing 10, 15, 20 lines of code, but something where you have to write a couple lines of code to fix a bug. So there are a couple of code reading problems. There's definitely problems there with binary search trees, AVL trees, some big O, and the code reading is more with the recursion. Okay. So questions about the final. Okay. So today we are wrapping up with big O and running time analysis. Also, I did just want to say one thing that I noticed about the exam and one thing that I've noticed about Lab 10. So several things there. So first of all, this actually does get back to running time analysis. On the exam, where you are asked to reverse the characters in a string, I'd say about a third of you wrote the reverse string function so that it returned, or reverse string helper actually, so that it returned a string. So at the very end of it, you had return S. Okay? This is something that you have to be very careful about with recursive functions. First of all, reverse string helper was doing an in-place modification to its parameters. So S was passed in, and you were doing an in-place change to it. So there was no reason to return anything. If you return something, you made the algorithm much slower than it needed to be. The reason is that to swap characters in the string, you swap 2 at a time. You only swap each character once. By itself, the swapping is just an order n operation. But when you return a string, the C++ compiler has to create an entirely new string from scratch. So each call now costs you order n. Before, each call was only order 1 because it just swapped 2 characters. But now each call is order n because you're constructing an n-character string. And to swap 2 characters at a time requires n divided by 2 calls. So you just turned your order n algorithm into an order n squared algorithm. And n squared is a lot worse in terms of its running time than order n. Okay? If you graph the two, this goes up in a straight line if it's order n. Order n squared goes up hugely faster. Takes a lot more time. So you need to be very careful about things like this when you're in recursive functions, because something that may seem innocuous, like returning a string, actually significantly increases the running time of your algorithm. It overwhelms what should have been a very efficient algorithm. Okay? So that's one thing where, again, we want you to be cognizant of running time. Okay, the second thing is on lab 10, which you're still writing. And there is a function called isAVL, where you're being asked to determine if a tree is a legitimate AVL tree. And if you remember the definition of an AVL tree, it's one where every node in the tree must be a valid AVL tree. So at every node, you're checking to see if the two children's height differs by 1 or less. And what I'm seeing is a lot of things with people writing height functions where they write a recursive height function. And they pass it a node n. And then in AVL, what they're doing is they are essentially saying they're making the call for the left and right trees. So they may be doing left equal isAVL, and I'm just using pseudocode here. So on the left subtree, and they may be doing right and doing the same call on the right subtree, and checking to see if the two are AVL trees. If one of them isn't, you already know you're not an AVL tree, so you simply pass the result back. But then what I'm seeing is left height equals recursive height, left subtree, and I'm seeing right height equals recursive, I'm just going to say, on the right subtree, and then the comparison of the two heights. This is bad because these two calls look at the entire left and right subtrees. They look at every node in the left and right subtrees. There's no need for that. Okay? If from isAVL you also return the height of the left and right subtrees, you don't have to, you can pass that information up from the leaves. You can start with 0, 0, 0, 0, and just pass up 1 and 1, and then pass up that to 2, rather than at 2 going down and looking at every node. There's 3 nodes in the right subtree, and there's 3 nodes in the left subtree, looking at all 6 nodes again, and then completely throwing away that information. And when you get up to here, again, doing a recursive call all the way down this right subtree and now looking at 7 nodes. And then when you get up to here, throwing that information all away and looking at everything in the right or in the left subtree. Okay, again, you turn what should be an order n algorithm into an order n squared algorithm by always calling recursive height. Okay, so you have to be more careful about these recursive calls because their running time adds up very quickly. Okay, so there is no reason to be calling recursive height in these two functions. You can return the height from your isAVL calls. What I did was you can combine it in 2 ways. Don't use a bool, return the height, and then return an impossible height if it's not an AVL tree. So you encode 2 pieces of information in the return value. If it's an impossible value for the height, and I won't tell you, but you should be able to figure out an impossible value for the height, then it's not an that subtree was not an AVL tree. Otherwise, what you get back is a valid AVL tree, and you're given the height of that AVL tree. And so what you return out of isAVL is either your impossible value, which indicates it's not a indicating invalid AVL tree, or you return the height. So isAVL is essentially returning the height, along with information as to whether it is a valid AVL tree or not. And that way, you end up with an order n algorithm rather than an order n squared algorithm. Okay, these things matter in the real world. Again, order n is much more efficient than order n squared. Okay? And very quickly, even on today's fast computers, you will notice when you have an order n squared algorithm, because things will slow down once you get to a few thousand objects. N squared becomes big enough that there will be a noticeable pause in the running time of your algorithm. It's not happening on your labs because we're not testing them with several thousand items. But in the real world, you would quickly notice the difference between an order n and an order n squared algorithm. So be careful with recursion. Okay, if you're not, the running times cumulatively add up very quickly. So questions about either of these, especially because you're still working on lab 10. Okay. So, next thing, just wanted to review, why did we spend a week and a half torturing you with AVL trees, which are a lot more complicated than regular binary search trees? The reason we did it is because AVL trees guarantee that the tree stays balanced. With no more than order log n levels, which means that your insert, find, and delete functions are guaranteed to have order log n running time. Okay, now, that doesn't mean you just blindly use AVL trees. The map and set data structures in the C++ library do use balanced trees because they do not know, they have to be generic. And so they have to work for all use cases. But if you were implementing one of these from scratch for a problem, you would really need to know in what order the data is coming in. So for the average case, where data arrives is inserted in a random order, AVL trees or BS trees are faster than AVL trees. That's most of the cases. So most of the time, binary search trees are faster than AVL trees because when the data comes in random order, binary search trees are also typically going to be log n levels. And they're not going to have all that overhead of rebalancing via rotations. So in general, binary search trees are faster than AVL trees. So if you have no reason to assume that the data is coming in almost sorted order, you actually would prefer to use binary search trees. It's only when the data arrives in almost sorted order, in sorted or almost sorted order, that AVL trees are faster. So again, we don't want you just blindly saying, oh, we'll always use a balanced tree like AVL trees. Now, if you use the map or the set data structure from the C++ library, that's fine. You have to use whatever they give you. But if you're doing something from scratch, you really need to know what is the use cases. Okay? Because most of the time, binary search trees are faster than AVL trees. They don't have as much overhead. Okay? So you need to distinguish between those two use cases. Questions about that? Okay. And the final thing, it's kind of neat to see it. We said that part of the reason to do a balanced tree is in the case where the data comes in order. So let's actually look at a situation where that happens, where the data comes in and it's completely ordered, and show how AVL trees actually manage to end up with a balanced tree. Because we know that in this case, a binary search tree would end up with a badly skewed right-leaning tree. It'd simply be a linked list. But if it's an AVL tree, comes in for the first two operations, it will be just like a binary search tree. On the third operation, we end up with what kind of imbalance? A zig-zig or a zigzag? Okay. And I will tell you, when it comes in sorted order, you always will have a zig-zig situation because it's the right tree that's always going to want to become bigger and bigger. So we will rebalance by rotating down the 1, so you'll end up with this tree after the insert of 3. Then you'll insert 4, and you're still balanced. Then you'll insert 5, and again, you have an imbalanced situation where you have a zig-zag situation. And the imbalance is right here at 3, so you're going to rotate about 4. So you're going to end up with 4, 3, 5. Okay, so now we go ahead and we insert 6. And is that balanced or imbalanced? It's imbalanced. If you do the heights, this is 0, this is 1, this is 0, this is 2, this is 0. So the imbalance is right here at node 2. It's a zig-zag, so we're going to rotate about the child of 2, which is 4. So the 2 comes down, and this tree is orphaned. It is adopted by 2, and 4 holds on to 5 and 6. Okay, so we're back to being balanced. So now we add 7, and I know this may look imbalanced, but I don't believe it is because the 5 is there and the 6 is there, so it's actually going to be a balanced tree still till we get around to putting 8 in. When we put in 8, we have the imbalance at 6, so we're going to come over and get 4, 2, 1, 3, 5, and we will rebalance. Whoops. We will rebalance by bringing the 7 up and the 6 and the 8 down. Okay, and this may look imbalanced, but if we do our computation, we'll see 0, 0. This is 1. 0, 0. This is 1. This is 2. There's no imbalance. So we're still balanced. I know it looks like we're slowly getting imbalanced, but we're still maintaining enough balance for the AVL condition. Okay, now when we add 9, yes, what? Yes. Yeah, you're right. It looks like we're imbalanced. Just a second. Very good. Thank you. Going too fast here. So, get rid of that. Okay, let me slow down. So 5, 6, I think it was actually imbalanced all the way back at 7. So let me get rid of that. Let me get rid of this. Thank you. So actually when we added 7, we were in balance because if we do the 0, 1, and now 5's left child is -1, so you're absolutely right. So we actually needed to do the rebalance earlier. So we'd have 4, 2, 1, 3, and we would rebalance by rotating about 6. We get 5 and 7. Okay, I'm going to stop here because you can see that actually we have gotten a completely balanced tree. Okay, so as we add 8 and 9, it's just going to essentially keep rebalancing into a pretty balanced tree. Well, you'll tend to get a little bit of skew when you add 8. You're okay. When you add 9, you'll again have to rebalance so that you'll end up with 8, 7, and 9. And when you add 10, I believe you will again get into a issue. If I'm not mistaken, you'll have 0, 1, 0. Yep. So you have to rebalance. But basically, the tree, I think when you get up to, it became a perfect tree at 8. I believe when you get to 16, it would again be a perfect tree. When you got to 32, I believe again it would be a perfect tree. Powers of 2, I think, I'd have to go through it the whole way, but I believe you'd keep getting perfect trees around powers of 2. Okay, so the rotations do work. They slowly bring the tree back into balance, and the rotations aren't always occurring at the bottommost nodes. So up here it occurred at 4, which is an interior node, and then down here it occurred at 5, which was an interior node. So they don't always occur right at the bottom of the tree. Sometimes they're further up the tree. Okay, but you can see that even with it inserting 1 through 10, this one's still in balance down here. I'd have to rebalance this one about 8, but when I was done with that, I would still have a rebalanced tree with 10 added. So you can see how AVL trees, even with something being given in sorted order, is able to keep the tree balanced. Okay, good with that? Okay, so take a deep breath, and we will head into the last topic. Before I do that, you'll remember at the beginning of the class, we gave you 4 objectives. We threw you in at the beginning with making you familiar with command line tools, so hopefully by now you feel pretty comfortable about using G++ and CD to a new directory and GDB, using ls to list directory contents. To become self-sufficient C++ programmers, so basically we reviewed C++ in the first month. We taught you about pointers. We've taught you about recursion. We've taught you more about how to debug programs. Okay? We forced you to do more printing. We forced you to use the STL libraries. So hopefully you feel more comfortable with C++ programming. We've gone through basic data structures, okay? Data structures that you had seen before were arrays and vectors. Data structures you had not seen before were things like lists and stacks and doubly ended queues and hash tables and AVL trees and binary search trees. So you learned about a bunch of new basic data structures, and the basic things were that we wanted to do find, delete, and insert, the 3 basic operations. We also have been talking about algorithm analysis, which is figuring out the running times of programs, and that's where we finish the course today with, again, looking at how you determine the running time of a program. Now, we've talked a bunch about big O notation and said, okay, the running time of a hash table is constant time on average. The worst case is order n. We've said the running time for find, insert, delete in a tree, a balanced tree, is order log n. And we've kind of said, in general, these are the running times, but we've never really looked carefully at how you go through a program and systematically do the bookkeeping required to determine its running time. So today we end with that, with how you look at a program and you determine its running time. Okay, and the book started that with section, I believe, 1.4, where it showed you a number of programs, and it would make you figure out the running times. One thing it didn't really dwell on is that when we are determining the running time, we have to make a couple of decisions. First of all, how do we count instructions? Okay, because some instructions take more time than other instructions. Cin and C out are relatively expensive compared to, say, a shift operation or an assignment. These are expensive. These are cheap. So are we going to try to differentiate between expensive and cheap operations? And the answer is no. It just doesn't, it's not worth it. And also, what we're really concerned about is what is called asymptotic running time. What happens as n gets really big. And as n gets really big, constant time operations like these really don't matter. So we just say that any instruction equals one time unit. And we don't try to quantify that time unit in terms of CPU speed. We don't say, well, one time unit equals 1 picosecond or 1 millisecond or 1 microsecond. We just say it's a time unit. Okay? So even if it is A equals B plus C times D minus E divided by F plus G, we say that that still takes one time unit, just like A equals B. And also that allows us to abstract away from the running times of different CPUs. Some of you have brand spanking new 2018 laptops in front of you. Some of you have older 2014 laptops in front of you. The ones running the 2018 laptops have faster CPUs. So we don't really want to have to analyze an algorithm on every single CPU because CPUs come in different shapes and sizes. So that's another reason to abstract away and just say one instruction equals one time unit. The other important thing is what do we make running time a function of? And we typically make running time a function of the size of the input because that running time is almost always a function of the size of the input because the bigger the input, it would make sense the longer the running time of the program. And usually, you will see the size of the input denoted as n. It's just an idiomatic that you normally see the size of the input denoted as n. Now, you sometimes have to figure out what n is. Okay? If I give you a string, and I ask you, so I say, okay, I'm going to do reverse string. And I give you a string S. Okay. That may not be as obvious. What is n? It is the size of the string. So in this case, n equals the number of characters in S. It should seem reasonable. The longer the string, the longer reverse string is going to take. We expect it's going to take more time to reverse a string with 10,000 characters than a string with 1 character. So here, n is equal to the number of characters in the string. Okay. What if I said that I was going to add vector or some vector, and I give you a vector v, well, int. Okay, now what is n? It's the size of the vector. So n equals the number of elements in v equals size of v. And it's the same thing here, equals the size of S. Okay? Now let's make it a little, this one is going to be, let's say some vector were instead vector of vector int. Actually, I'll change it a bit. Let's say that this was one of your PGM labs from earlier. So you were doing some picture operation like let's say you were doing crop. And you were given a vector of ints, which was a PGM file. Now what might be the size of it? It is the entire thing. Good, John. So it is still the number of elements in the PGM. But now we have to have a kind of more succinct way of talking about it. And what we normally now say is that it has m rows and n columns, or you may reverse it. And so we'd actually say it was order mn, where m was the number of rows and n was the number of columns. So instead of saying it's just order n, where n is the number of elements, we actually tend to be a little more fine-grained, and we talk about it in terms of the number of rows and the number of columns. So sometimes the input actually depends on two different values. And then typically the second parameter that we use is m. It's just, I think it's from the mathematicians, but that's just how it is. M then becomes the second one. Okay, this can also come up when I am doing some number of, let's say that I have some program where I do some number of lookups and some number of inserts. Okay, and let's say that for whatever reason, inserts take order 1 time, but lookups take log n time. In that case, where n is the size of the input. Well, now you need to know something else. It's not just so the number of inserts is the size of the input. So we know that the number of inserts is n, because that's the size of the input. But that's not the end of the story. Because the lookups take log n time. So we know that we have n times order 1 for the inserts, but the lookups are log n. You can't just say that the program takes n time until you know how many log n lookups are required. If it's a constant number, c, then we know that the running time is equal to order n because this term dominates. If the number is n, then the running time becomes n log n because the lookups predominate. But what if the number of lookups is unrelated to the number of inserted elements? Then we say the number of lookups is equal to m because it's a different number than n. We don't know how many or how few, and so we have to use a different variable to represent the number of lookups. And in that case, we could not know. And so we would end up saying that our running time was actually n plus m log n, because we don't know in this case which of the two terms is bigger. This is the one time you would actually see more than one term in the big O notation because we don't know which is bigger, N or M. Now, for this class, we're not really going to worry about N or M, but I do want to show you that the size of the input is not always just a function of one variable. Sometimes the size of the input depends on multiple variables. And in that case, we use two different variables to account for that fluctuating sizes. And sometimes because they're not comparable, the N and the M aren't comparable, both of them end up in our big O notation. So I just want to introduce you to that fact. Okay, so quick review. We assume every instruction takes one time unit without ascribing any particular clock time to that time unit. We just say one time unit per instruction. And we use N typically to denote the size of our input, but if there are multiple variables determining the size of the input, typically M would be the second variable we would use to denote size. Okay, so then when we're looking at instructions, there's a number of rules that we apply. Okay, and the book kind of talks about them. So the first one is that when you have a series of sequential operations, so I'll call these the bookkeeping rules for determining time. So now we're trying to count the number of time units. The whole idea is we wanted to come up with a function T of n that describes the running time. The book uses f of m, but typically it's T of n for time. And you want to come up with a fairly exact function describing the number of instructions as a function of n. Well, generally, each instruction takes one time unit, so we'd say that when they are in sequence, we simply add them up. So instructions in sequence are simply summed up. So there's two instructions in this sequence, therefore their running time is 2 time units, 1 time unit each. Okay, loops are the next one. And roughly speaking, the number of instructions in a loop equals the number of loop iterations times the number of, the number of instructions in the loop body, or in each loop iteration. And you have to count in the loop iteration both the loop body, the test, and the increment, if there's any. So in a for loop, there's always a test and an increment. So you can't just count the loop body, you also have to count the instructions associated with the test and the increment. So here, there were 2 instructions in the loop body, so that's 2. This is 1 because that's a conditional check. So in fact, there are 3 instructions in every iteration. And because we're going from, it looks like I equals 0 to n, there are 3 times n instructions in the loop. So it might look casually like the right answer here is going to be 3n plus 2. But that would be wrong. Because if you're doing a very close accounting, this instruction right here executes n plus 1 times. The very last time the loop does not execute. When I goes from 0, then it becomes 1, 2, eventually I becomes n. And when I is equal to n, we exit the loop. But that means that this condition is checked n plus 1 times, not n times. Therefore, the actual running time of the loop is 3 times n plus 1. Because that last time you check the loop condition, it's false, but you still had to check it. So the right answer actually was 3n plus 3. Now, I will not be this cruel to you on an exam. Okay? This kind of bookkeeping is really picayune. But I'm just showing you that if you're doing a very precise accounting, this is how you would have to do it. You'd really have to look carefully at each instruction. Okay? Now, there are two more important things. So everyone got bookkeeping rules 1 and 2? Okay? What if you have an if then else? If condition, true block. The book doesn't have any, that's why I'm not. Else, false block. What we do in this case is we have to assume that the worst case happens because we don't know in advance whether it's the best or worst case. Now, if it's an error case, we tend to assume the error case doesn't happen. But otherwise, if it's a normal thing where either the true block could execute or the false block, we have to assume the worst. So what we do is we say that here that the running time of an if statement equals the time for the conditional. So the number of instructions, we'll say the number of instructions for the conditional plus the max of the instructions for true and instructions for false. So we assume the worst. We assume the longer block always executes. And then we add the instructions for the condition. Normally, the condition is just one instruction. But let's say we said if is AVL. Do something here, else do something here. Well, that brings us to rule 4. If the instruction is a function, it is the one time. If the instruction is a function call, we don't assume it's one time unit. Then running time is the number of instructions in the function. And if that function makes recursive calls, we have to add in those time units too. So that's where it's important that you write a very efficient function for isAVL because you're charged however many instructions that takes. If you wrote an order n squared algorithm for isABL, you would be charged order n squared time for that conditional check. If you only took n time, you would be charged order n for that conditional check. So the condition is typically just one instruction, but sometimes if it's a function call, then it's the cost of that function call. In fact, in midterm 2, when you were inserting a person into the map, you only did it if they weren't already there, and that required a find. And so many of you had if find. That cost you log n, and many of you didn't realize how expensive that was, and so you called find a second time. And I told you that wasn't good because the find wasn't free. It wasn't a single time unit. It was a log n operation. So these are the 4 rules that you use for counting. Now, to get that super picayune thing, which is what the book was doing, doesn't really work. Especially, it can get a lot more picayune. Let's say you had for I equals 0, I less than n, I plus plus. And now you have for j equals I, j less than n, j plus plus. Well, now you're really kind of up against it, right? Because how many instructions does this loop take? I just told you it's the number of instructions times the loop body. I'll make it simple. I'll just say sum plus equals j. So there's one instruction in the loop body, there's the test, and there's the increment, which essentially makes 3 instructions per iteration. But the number of iterations depends on I. So when I is 0, there are n iterations. When I is 1, there's n minus 1 iterations for j. When I is 2, there's n minus 2 iterations. So we have 3 times n, 3 times n minus 1, 3 times n minus 2. Eventually, I becomes equal to n minus 1, and this gets down to 3 times 1. So what we really end up with is 3 times 1 plus 2 plus ... plus n minus 2 plus n minus 1 plus n. And now you have to be able to sum up that nifty little sequence. And there's a trick to summing that sequence. Anyone know the trick? No one's seen the trick? That's fine. I'm just curious whether in any of the math classes they showed you the trick.
Is it where you basically add everything up like backwards? So you would take a 1, for like 1 you would add n.
Very good.
To 2 you would add n minus 1.
Yep, very good. You got the trick. So the trick is look at the first and the last pairs, 1 and n. Look at the second and the last pairs, 2 and n minus 1. Look at the third and the 3 and n minus 2. What do they all add up to? N plus 1. How many such pairs are there? If there's n numbers, how many pairs? N divided by 2. So that's the sum. So when you have the sum of I equals 1 to n of I, it turns out that it is equal to n times n plus 1 over 2. It's a trick. Someone doesn't show you the trick, you're unlikely to see it. I was just curious whether any Where did you see the trick, or did you just figure it out?
My math teacher
Okay.
has both
In high school or college? Here, okay. So I was just curious. This is a discrete math trick, and in calculus, you're dealing more with continuous sequences. So you may never have seen the trick in any of the calculus classes. So this is why you take CS 311, because there is discrete math like this, where you need to be able to sum up sequences. This is an important sequence that comes up a lot in computer science. And that's how you get it. Okay? So it turns out that this loop requires essentially 3 times n, because that's the total number of iterations that it made. Now, I conveniently left out the fact that each iteration also had a final check at the end of j. I'm sorry, when j got equal to n. So really, each iteration was 3n plus 1, 3n minus 1 plus 1. What a pain in the neck. So it was really n plus that, because this for loop got executed n times, and there was one extra check. That's why we don't get super picayune. It's just hard to account for every instruction. And all we end up caring about is the big O running time. So we don't have to be picayune. We can take a meat cleaver to this thing. Okay? No one cares about that n. Why does no one care about that n if we're caring about big O? What's the elephant in the room, or in that expression? N squared's the elephant in that expression. No one cares about a measly n. Okay? So no one cares about these constants. Okay? All we care about is this term right there, the big N squared. So it was important that you could do this summation, though, it turns out, because it's important that you know that you can't just say, oh, that executes n times and that executes n times, so it's n squared. It wasn't quite that simple. You have to be able to sometimes do a little bit of more sophisticated calculation, because this inner for loop didn't always run n times. And you can't just say, oh, I'm going to assume that that it always runs for n times. I'm going to assume the worst case that it always runs for n. No, there you have to be a little more careful about how many times the loop is running. But we still came out to n squared. So the reason we don't get all picayune is because when we were calculating this, so let me just go back to our original expression. We were looking at this. This doesn't matter. All that really mattered was that we had n iterations times a constant number of instructions per iteration. So when it's all said and done, we actually just say that when we have a sequence of constant time instructions, remember rule 1, we just end up saying that it takes order 1 time. A sequence of constant time instructions takes order 1 time. All we really care about is loops, and with recursion, which recursion is a kind of looping. Like when you did the reversal of the string, that recursion was really a bit like a loop that was running from I equals 0 up to where start character was greater than end character. So with recursion, you care about the number of recursive calls. So you were given selection, sort, insertion. Today you looked at, with sorting, you looked at insertion sort, selection sort, and quick sort. Those were the three sorting algorithms in your assigned reading for today. Okay? Well, if we just quickly look at those three, actually before we do that, I want to do one more thing that's important. Let's say that I wrote this. What is the running time of this particular piece of code? I heard it. It's constant. That is order one. You're looking at that like, what? You kidding me? It's order one. Why? It doesn't matter how big n is. N's irrelevant here. The answer is 100,000 times n. You're running the loops 100,000 times. No matter how large n is, how big or how small n is, the inner loop runs 1,000 times for each iteration of the outer loop. So the inner loop is 1,000 iterations. Okay, the outer loop runs 100 iterations. So there's 100 times 1,000. That's equal to 100,000. There's 100,000 iterations there. Doesn't matter how big or how small n is. It's irrelevant. Those loops run 100,000 times. It's order one. I know that's a huge constant, but it's order one. It's constant time. As n goes to infinity, if we map that puppy, as n goes to infinity, running time, flat line. It's constant. Okay? So if I were to put that little cute thing on the exam, I would expect you to say constant time and not be fooled by that sum plus equals n. Okay? I think the book even somewhere, they may have. They did? Okay, good. They had that kind of funny, yeah, there it is. For I equals 0, I less than 24. That's constant time. Okay, that was a constant time. Else if time hour, it didn't matter. For I equals 0, I less than 24. Everything's a constant there. That was a constant time piece of code. Okay, so this whole thing right here was one big constant. It ran in order one time. So that's what I care about. I actually don't care that you come up with T of n equals 3n squared plus 5n plus 6. What I care about is you can figure out what is the meat cleaver. What is the biggest term in the function? That's important. That's basically coming down to your loops and your recursive calls. Okay? Now, some of those loops may be in your functions. Okay? The other thing is you sometimes have log n. So, for example, whenever you have a tree or you're having something, like in binary search, that's log n. If I have for I equals n, I greater than 0, I equals I divided by 2. That is not a order n loop. This executes, this is log n iterations. Whenever you're having the input, that's log n. Whenever you have the input, it is log n. Okay? So now we can take a quick look at those three sorting algorithms that you had. So it started with selection sort. And that was not the complete algorithm. So here was the complete algorithm. You had an array of numbers that you are sorting. So first of all, you have to determine what is the size of your input. The size of your input here, n, equals the size of numbers. So it's the number of elements in that array. Okay? So number size was actually the size of that numbers array. So when they said for I equals 0, I less than number size minus 1, they were really saying for I equals 0, I less than n minus 1 was effectively what they were saying. So that's where you're not just, someone's not going to, like me, is not going to be nice on an exam and just put n in there for you. You have to figure out what n is, okay? So in this case, number size is really n. Okay, so we're looking at essentially that number of iterations for the outer loop. That's a constant time instruction. Now we have the 4, and oops, there's that nasty I plus 1 again. And j less than essentially n. Well, fortunately, Dr. van der Zanden just went over what happens when you have j equals I plus 1 up to n. He showed us that cute counting technique where the first time through, j has 1 iteration, the second time it's 2, the third time it's 3, all the way up in this case to n minus 1. And we know that that is equal to n times n minus 1 over 2. So we know that the big number there is n squared. So we know that the number of iterations through here, the number of iterations is always n minus I. This if statement is constant. So there's a constant number of instructions in each iteration of that for loop. So the for loop, the inner one takes 1 times n minus I time. The outer loop executes n minus 1 times. We did this little summation. We know that the total number of iterations is n squared. So we know that this entire, and then this right here, 3 instructions, order 1. Constant time. So everything in the loop is constant time. All we care about, therefore, is the number of loop iterations. The number of loop iterations is n squared. Hence, the running time of that algorithm, selection sort, is n squared. Okay? So that's selection sort. Questions about that? Okay, so we move on. I'm not going over the specifics. You should have read it. If you didn't, well, you can read it later. Okay, so we do insertion sort. And again, that's the big thing we're sorting. So it's the number n equals number size, the size of that array. Again, the outer loop for I equals 1 to number size, so roughly n iterations. It's really n minus 1 iterations because we started at 1, but that's not really, again, we can use a meat cleaver approach. We don't really care. Roughly speaking, there are n iterations. Trying to say approximately here. There's approximately n iterations. Okay? This one is a lot nastier. While j is greater than 0, so j starts out at I. So the first time through, j starts at 1, then j will be 2, then j will be 3, then j will be 4, all the way up to n minus 1. While j greater than 0 and number j is less than numbers of j minus 1. So basically, with insertion sort, we keep moving back through the array until we find where the item goes. So if we have thus far 3, 6, 8, 10, and the number that we're inserting is 5, we have to go all the way back to between 3 and 6. So it's unclear how far back we're going to go. We could get lucky and have 13, which requires no movement, or we could be unlucky and have 1 and have to go all the way to the very beginning. So what do you think we have to assume in this case? Do we assume the best case? No. What do we assume? The worst case. So we have to assume, not knowing anything else, that it's going to go all the way to the beginning. This is where we can talk about also both worst case and average case. On average, how far do we go? The middle. On average, we'll go to the middle. So this is a situation where the worst and average cases are different. So then you also need to know, do I care about average case or worst case? Well, we kind of like to know both. Fortunately, it doesn't really matter. Okay, in one case, in the worst case, we have to look at I. So in the worst case, it's going to be, we'll look at 1, 2, 3, all the way up to n minus 1. In the average case, it will be half that. Okay, so in the worst case, when we sum these up, we get n minus 1 times n divided by 2. That's the worst case. And the average case, where we divide everything by 2 and only go halfway, if I know the worst case is n minus 1 times n divided by 2, what is the average case? N minus 1 times n divided by 4. It doesn't matter. We don't care whether the constant is 1/2 or 1/4. They both give us n squared. And everything else in our thing was, again, constant. There was 4 constant time instructions in there, which made it order 1. The j equals I was order 1. So everything else was order 1. So we end up with order n squared being both the worst case and the average case for insertion sort. Okay, and we won't worry about the times for, quick sort. That's a little more complicated. We'll let that go for 302. Okay, so that's it. All right. We will see you all on, thank you. We will see you all on Thursday. Just sleep in until 8:45.